Hello, everyone. Welcome to my talk. Today, I will talk about how to build a unifying machine learning pipeline with XGBoost and Spark. My name is Nan Zhu. I'm a software engineer from Microsoft. In Microsoft, I work on integrate Spark streaming, thread streaming with Azure Event Hubs, which is a real-time message ingestion service on Azure. And my colleague and I will give another talk on this topic at 5 p.m. today. So welcome to that talk as well. I also work on test, monitoring, and optimization for Spark workload performance. I serve as a committee member of Apache MaxNet and DMLC. I also contribute to Spark. So about DMLC, Distributed Machine Learning Community, we are a group of engineers, researchers from different organizations. We collaborate on open source machine learning projects. Some of the projects we build like XGBoost, which is a major topic today, and MaxNet, which is one of the most popular deep learning frameworks. So in today's talk, I will first introduce XGBoost and XGBoost Spark. I will talk about the project history, some brief introduction about how XGBoost works. But due to the time limitation here, I will not go into algorithm details and formula derivations. We have a paper on KDD 2016 with plenty of details about the algorithm. If you are interested in that, you can read it. And I will go into details about why we want to integrate the XGBoost and the Spark, or say what's the real problem we want to resolve by integrating these two systems. And I will give more details about the design of XGBoost. And finally, we will have a brief discussion on what we can learn from XGBoost Spark design. So this is my personal contribution to XGBoost project. And what is XGBoost? XGBoost is a gradient booster tree implementation. It was created by Tianqi Chen, who is a PhD student in University of Washington in 2014. And until today, it has been more and more mature. It provides bindings for different programming languages. You can run XGBoost on single machine, distributed machines, and you can run it with GPU. For XGBoost Spark, it is the real effort to integrate XGBoost and Spark. The idea was generated in a discussion in NIPS 2015 between Tianqi and me. And in March of 2016, we released the first version of XGBoost Spark, which is based on RDD. And after the summer of the same year, we have the second version, which is based on DataFrame and ML framework. We have a growing community around XGBoost. More than half of winning solutions in Kaggle competition are using XGBoost. And for XGBoost Spark, we attract a lot of users from different companies, like Airbnb, Microsoft, Uber. And our developers are from University of Washington, Microsoft, Uptake, and some other companies. So then let's go technically deeper to introduce XGBoost. As I said, XGBoost is a gradient boost decision tree implementation. To understand this concept, I will separate it into three parts. First, what is a decision tree? And second, what is a boosted decision trees? And third, what is a gradient boosted decision tree? For decision tree, in XGBoost, we adopt one type of decision tree models called classification and regression trees. Like many other decision tree models, a card assigns the data points to the leaf node of a tree structure based on the rule on different levels of the tree. For example, here, we work on a problem like we want to predict whether this person will like computer games. So we have a first rule on the root level, which separates the data sets based on the age of the person. And then in the lower level, in the younger group, maybe because of that, a lot of games are not properly tailored to girls' interest, we can separate the data sets further based on the gender of the person. And specific to card classification and regression tree, it will assign a score to the leaf node of this tree. and the data points associating with that leaf node will get that score and use that score as a base to answer a predictive question. And here, the youngest boy gets the +2. It means that he is mostly like computer games. Then what is decision tree boosting? Decision tree boosting means that in our machine learning model, we use more than one trees. For example, here, we introduce a new tree which separates the data sets into two parts with a new rule that is based on whether this person will use computer daily. And specific to a single data point, the overall score it gets from these multi-tree models is the sum of all scores it gets from every tree. So the idea here is called ensemble learning in a general machine learning context. That means we use multiple weaker learners to achieve better performance than anyone alone. And in XGBoost, for each iteration, we will build a new tree. The remaining question is that specific to each iteration, or say each tree, how can we determine the shape of this tree is the optimal one we want to get? Then it involves the third part about of our introduction to XGBoost. What is the gradient booster tree? Before I introduce gradient booster tree, let's review some concepts in supervised learning. Supervised learning means that we have some labeled samples from certain data distribution, and our task is to find a function to describe this distribution based on our observations. These observations are those labeled samples. So to achieve the goal, we introduce an objective function here. This objective function contains two parts. First is training loss. This part measures how well our model will fit with those labeled samples. That's the training data. And the second item is called a regularization item. It controls the complexity of the model because we only get some samples from that distribution. We don't want to build a model which is too complex, which can meet with those labeled samples well, but ignore those unobserved samples in the same distribution. And in XGBoost, we also have this objective function. That means in each iteration, we want to find a function which represents the optimal tree structure we want to get in this iteration. So how to find this function? We have to answer two questions here. First, specific to this tree, how to determine the score on the leaf node. So the idea here is that the first step for us is to represent the object function as something related to the score on the leaf node. So here we define the function as a vector of the score of the leaves, and another function which maps the data points to certain leaf node. And for regularization item, we define it as the number of nodes and plus the sum of the squared scores of the leaf nodes. And then we can transform our objective function as something related to the score. And after a chain of transformations, we can get the optimal value of the score and the smallest value of objective function. And I will not go into how to derive that. If you are interested in that, read our KDD 2016 papers. And the second question to design the tree structure is how to decide the best splitting point for a specific node in this tree structure. For example, here, why we want to separate the root node at 15. The idea is that since each node will associate with a lot of training samples, and for each feature, these samples may present some continuous values. We want to avoid enumerate each value to find the best split. So we propose we transform the continuous feature values as discrete buckets. And then these buckets should pursue mostly even data distribution. And among these buckets, the boundary of these buckets, we will take the one which brings the largest loss reduction. So how to achieve this are also described with details in the paper. So if you're interested, read our papers. We also have other optimizations in XGBoost. We can build a tree with multi-threads. We can scale the training with disk space. You can also train in a distributed way. So we have talked about so many good things about XGBoost. So let's build a machine learning pipeline in production with XGBoost. So how to do that? First, when we build a machine learning pipeline, we have some raw data with different formats in different places. And this raw data may be broken. They have duplicate columns. They have missing values. We have to clean it. So Spark is one of the best tools for us to do data cleaning. And then maybe you have different teams in your organizations, or you have a different preference. You have to save the cleaned data in different formats in different places. Finally, we can introduce XGBoost here. Load the training data, build the model. Don't forget that XGBoost is just a component in your overall infrastructure. You have to make XGBoost collaborate with your supporting infrastructure. And for your trained model, you have to output in a certain format to serve in production. And because we want to make XGBoost to load different format of data to coordinate with our supporting infrastructure, we have to introduce a lot of glue code to bind XGBoost in your infrastructure. And in in NIPS 2015, there is a famous paper from Google team. They point out that a matrix system might end up with at most 5% of machine learning core code. The XGBoost is a machine learning core code. And it will be with at least 95% of glue code. And unfortunately, this glue code is costly in long term, because it will bind your infrastructure with a certain machine learning core code, and it will be very hard for you to test alternatives. So how to resolve this problem? Let's review the design of another system which we might be more familiar with. That's Spark MLLIB. For Spark MLLIB, it provides a framework for different machine learning algorithms. These algorithms access outside data with a standard Spark SQL API. And because these algorithms run within the framework, we don't need to introduce any additional glue code here, since Spark has handled everything. And additionally, Spark ML framework provides a set of tools for us to do feature engineering, tuning, and a lot of other tasks. So the idea here is very clear. Our goal is to make XGBoost run as a native algorithm in Spark ML framework. So how can we do that? First, we know that Spark is a cluster computing framework, and it is centered on RDD. So our first mission is to make XGBoost and Spark communicate in execution and memory layer. So for execution layer, let's first review how distributed training with XGBoost works. In XGBoost, we have a central control process called tracker, and we have distributed workers. And then for each worker, it will take a partition of training data, and locally, it will compute some local states. And then, with our reduced algorithm, it will synchronize these states. And finally, with those synchronous states, it will grow the tree. Our task is to run this model in Spark cluster. The first thing for us to do is to start the tracker in driver side. In driver side, we start a tracker with a Fox process. And then in executor side, in each Spark task, we will start the XGBoost worker with a JNI interface with a Scala code. And then these workers will communicate with each other with the original or reduced layer in XGBoost. This is in execution layer. Then in memory layer, because we want to make XGBoost and Spark communicate between native memory space and RDD memory space. So we just copy the data with the JNI interface from RDD memory space to native memory space and train the model and get the model in Java heap space. One of the implementation details here is that JNI calling is very expensive. We don't want to copy sample by sample. So here we copy in batches, and then with the native code, we will interpret this memory batch and transform it to the format which can be read by native code, native core code of XGBoost. So all of these details will be wrapped by our API. For example, here, users can load the data with the standard Spark SQL API, and then with the plain Scala code, it configures XGBoost. And finally, with our one-line API, it just train the model, get that, and do prediction. Now we can run XGBoost within Spark cluster. The next thing is how to integrate Spark ML framework. Because ML framework provides so many good things, feature engineering tools, pipelining, persistence tools. So how to integrate with this framework? Let's first review how the machine learning pipeline looks like with the Spark ML framework. First, we have some raw data, and through first set of transformers, we can pre-process those data. These transformers can be string index. For example, it will transform the categorical string features into numerical index and with a one-hot encoder. And finally, we arrive to estimator. This estimator will produce another transformer. Sorry, that is actually the model we want to train. And then with this model, we can do some prediction result. We can get a prediction result. And this pipeline is separated into two parts. First is the training, and the second is the prediction. And in many cases, we want to use prediction result to feed it back to the training phase and tune our models. So then our first task is to how to make XGBoost train as a native Spark ML algorithm. And here we implement Spark XGBoost estimator by extending Spark ML's estimator class and trigger the distributed workers. And next, how to make XGBoost predict as a native Spark ML model. And we implement XGBoost model by extending the transformer framework. And finally, how to make XGBoost tunable as a native Spark ML algorithm. So we implement XGBoost parameter system and make it accessible by many tools in Spark ML framework. Because we implement all these things, we can build a full machine learning pipeline with XGBoost and Spark ML framework. Here is the example. For example, first, we build some pre-processing pipeline. All of these are done with Spark ML's utils and APIs. And then we search the optimal parameters for XGBoost with the cross-validation tool. This is also from ML framework. And we evaluate the performance of XGBoost with the Spark GPT classifier. We use an airline data set. We combine several years together, and we run it on Azure. Then we can see XGBoost is 10 times faster than Spark GPT classifier. We're also improving the efficiency of XGBoost Spark. Here, one of the important work we are doing is a unified memory space. As we said, we always copy the data from RDD space to native memory space, and it will increase the memory footprint. Now we are trying to use Apache Arrow to share the memory space between RDD space and the XGBoost workers so that we don't need to copy data. So the last topic of today's talk is about what we can learn from the design of XGBoost Spark. We can see Spark ML framework facilitates us to implement something like XGBoost Spark. We can use those more efficient algorithm implementation with in Spark ML framework. But building a machine learning pipeline is far beyond that. We have more pain points in that. For example, system behavior is tightly binded with the other input, like data, like especially when your input is from another machine learning model. And also, we depend on the data. Maybe we want to vision our training data set to avoid like a trained model with some immature data set. So all of this can be done in the future development of ML framework or some other framework on top of current Spark ML framework. So in today's talk, I introduced XGBoost and XGBoost Spark. And we also discussed machine learning algorithm is actually a very small part of the complete data processing or analytic pipeline. And we show an example about how to resolve this headache. We embed XGBoost to ML framework to do that. And we also have a brief discussion about what's our new expectations to Spark and Spark ML framework. So finally, let me give special thanks to Tianqi, who created the XGBoost project and offered a strong support when I built XGBoost Spark. And also thanks to XGBoost committers, contributors, and users who keep working on improving this project. And also thanks to McGill University, where I get my degree, which supported me working on this project. So this is the URL of our GitHub repo and JVM packages. And thank you very much. Questions?
This is more like a comment. I'm not sure if you are familiar with deep learning for J. It's a deep learning framework on top of Spark. They are using ND4J, which is also
ND4J.
Yeah, which is also a JVM J9 interface to off-heap memory. So maybe you can use that. So I think they're just holding a reference to a off-heap memory address in their data frame or their RDD, and most of the data is in native memory. So I guess it could be an alternative to Apache Arrow. So maybe it's something that you could look into.
What's the question? How to?
So this is just more like a comment rather than a question.
Okay. You mean how to integrate with Apache Arrow?
No, I mean this is, ND4J might be an alternative to Apache Arrow for Spark and off-heap memory interaction.
What that?
No,
okay,
let's sync offline. Yeah.
Okay, let's talk offline.
Yeah.
Hi, how do you actually use this in Spark? Is that like a dependency I just put in my POM, or how do you use this in Spark code?
How we use that in Spark?
Yeah. Like how do you bring this package into Spark? Is this like a separate package? I can just mention it in my Maven POM, and then I have all the things available?
For use this, you just compare, because our package depends on Spark, you just compare that, package that, and the native library is also in the package jars, and then you can run it in your cluster.
So I can just add this jar to my Spark code. Okay.
Hey, sorry, forgive me if I'm behind the times, but Spark, XGBoost on Spark does not yet support the ranking functionality of XGBoost standalone. Do you know if anyone's working on a contribution for that?
It supports now, just like several weeks ago.
Nice, right on. And one more thing, so just operational type stuff. Spitting out a PMML file from SparkML now, that's still, that works through the, can you spit out a PMML file from Spark on XGBoost on Spark?
I'm sorry?
Can you spit out a PMML file? You mentioned part of the glue code, right? Is spitting out something to productionalize the code. So does using, are you able to spit out a PMML file from?
The PM pipeline?
Yeah, as part of, from the package. Like a lot of SparkML type algorithms can spit out the model in PMML form. Can I use XGBoost on Spark and spit out a PMML file from it?
Yeah.
Cool. How? I'll talk to you. I can meet you.
How to do that?
Yeah.
So your goal is to use XGBoost with the. Okay, let's discuss offline.
I have a question. So does this support Can I run this in Java Spark, or does it only support Scala Spark?
Currently, it only supports Scala, and potentially you can call with Java, but no Python package.
No what?
No, we only have Scala bindings right now.
Okay. Okay, cool, thanks.
So there are lots of parameters that you can set for XGBoost. I was
Yes.
wondering how you do hyperparameter search.
Generally, we have some like guidance on tuning XGBoost. Like there are several most important ones. In most of cases, you just need to tune that. And in some corner cases, you may want to involve other things. So with this, you can like, I think 3 or 5 are most important ones. Just set it with ML's API and let cross-validation to help you to do that. So you.
Another question. So the cross-validation is not for Spark, right?
What?
Is cross-validation working with Spark? Because I think it's for the like non-Spark JVM packages, as far as I know.
Can we support the non-Spark?
No. Can you use cross-validation with Spark package of XGBoost?
No. No, sorry.
And another question, have you tried to like sort of do cross-validation with a Spark and for some long-running jobs? Because I have tried to do that, and I've seen some memory leaks for the Spark version.
Is there any memory leaks?
Yeah.
Until so far, when I tried many times, I didn't see that. Regarding memory, the biggest issue in current implementation is we need to copy data, and that's a large memory footprint. So that's a big problem. For memory leaks, I haven't found that.
Hi.
Hi.
Last year, when some of this work came out, a number of people tried using it and found very significant slowdowns as number of nodes goes up.
The training speed is slowed down?
Training speed substantially sublinear growth. Has a cause for that been discovered? Has there been changes recently to make that go away?
There is some cost because of the or-reduce operation on each iteration. So when you are increasing the nodes or computing resource, you will have more requirement to synchronize among all of them. So that will become the biggest cost, because on each worker, you will have less training samples to train, and the computation would not be the bottleneck. So in that case, the scalability is not that well. So that's kind of we expected, but of course, we can improve that or reduce operation.
So is your advice to try to train with as large nodes as possible and as few of them in the Spark cluster scenario? As a default?
You mean if we want to fully utilize that, is it just stuck at a certain size?
I'm looking for your advice on how to configure clusters for optimal training performance.
Based on your training dataset size, and based on your training dataset size and your feature size, I mean the dimension of your feature vectors, we don't have any like offshore guidance to tune that. You have to experiment and see what's the bottleneck. Most of the cases, when you have less data, you will not want to use a lot of workers on that, because, as I said, communication is a bottleneck. The other advice is you can explore to assign more CPUs to each Spark task. If you are stuck at a computing part, by assigning more CPUs and compare with OpenMP, then it will utilize like multi-threads to build each tree. Then that will accelerate your overall training. So that's for when you're stuck at computing and when you're stuck at the communication.
I think there are more questions, but let's take it offline and thank the speaker again.
Okay, thank you.